Friday when we were looking at sinusoidal waves, where we had nice, easy sinusoidal waves. Today we're going to be looking at harmonic motion. So if you're a physics student, an engineering student, you're going to be needing to understand the harmonic motion. It's still going to be sine and cosine, but some of the things that are happening here are more than just my amplitude. You'll notice the way that I define my amplitude, I need to have an initial position, I need to have an initial velocity, and I need something called omega. So as I go through this, we see the initial position right there is the position of equilibrium. And I'll show you some pictures of what I mean by equilibrium and where that is. We need to know the velocity of our mass that we're looking at, our item that we're looking at. So when we talk about velocity and we're talking about a spring, if I pull that down and let go, that's an initial velocity. How fast it goes back up would be the initial velocity. So these will have velocity to them. The thing that we're also going to be looking at is the omega. So that'll be the change in which, like we have before, it'll be the change of our period. So that's nothing new. So, but our omega here is defined as K divided by M, where M is the mass and K is the spring constant. Okay? So when we're talking about the force, we are talking about the mass of the object multiplied by the acceleration. Mass times acceleration. The weight, when we talk about weight, it is the mass of the object, and then since we're on the Earth, it is the gravity of Earth. Gravity in metric is 9.8 meters per second, and in imperial, which is what we typically use because we're a little backwards in the United States, we use 32 feet per second. Okay, so these are gravitational constants on Earth. Any questions so far?
Yeah, what was K again?
So K is the spring constant.
And M is the mass?
M is the mass. So when we're talking about the spring constant, we're talking about how stretchy it is. How easy is it for it to stretch? Some springs are going to be easier to stretch than others. So that's what the spring constant refers to, is how easy is this to stretch.
So there's like a gradual decrease in velocity based on the K?
Yeah, so when you pull an object down on a spring, it's not going to continuously have the same distance from equilibrium, right? As it starts to come down, it will eventually come to equilibrium. So that's why we call this the undampened harmonic motion, is that for ours, we're going to assume it's not going to dampen down in real life. It does. So what I mean by that is, in real life, if you were to graph your spring, right? So you pull it down, and then it's going to come back up, and then it's going to go down, and eventually it's going to come down to where it's not moving at all. That's a dampened harmonic motion. For us, we're going to have undampened, which means as we are doing it, it's going to continuously do this, and that the spring doesn't change, which we know isn't in real life. Okay? Does that answer your questions on those? Okay. So a couple of things that we need to talk about is acceleration is distance divided by time squared. Gravity is acceleration because gravity is some distance, 9.8 or 32, and then it is meters or feet per second. So the acceleration is gravity. Hooke's law states that the force is equal to K, the spring constant, multiplied by D. And that's the distance from equilibrium. So force is the spring's constant multiplied by the distance from equilibrium, the item moved. We also have some units here. So the units, 1 slug, being in the Pacific Northwest, that's not those things that are about 2 inches long and kind of green-gray. That is not what we're talking about. Those are gross, by the way. 1 slug is 1 pound-foot second squared divided by feet. 1 pound-foot. Yes?
Can you explain a little bit how gravity is acceleration?
So gravity is the distance traveled divided by seconds squared.
Gravity is a distance or a force?
Gravity is both. So gravity is acceleration. So when we talk about acceleration is, like if you have something in your hand and you let it go, that item initially has no velocity and it has no acceleration. But you let that item go, it's going to start going toward the earth with a velocity increasing. If your velocity is increasing, that means it must have an acceleration on it. And the acceleration on it happens to be gravity. Unless you're throwing that item on the ground, you just have something and you let it go, then it has no initial velocity and has no initial acceleration, but when you let it go, it starts to go toward the ground. And as it goes toward the ground, the initial velocity is 0, but when it hits the ground, it's going to have a velocity more than 0, which means it had to have acceleration on it. And that's why gravity is both a force and an acceleration. Does that explain? Okay. All right, so when we're talking about equilibrium, here's an example of a spring here. It's a real simple spring here, and you can see the masses underneath it. So at equilibrium, that means that the spring is neither stretched nor compressed. It just has the item attached to it. If you pull it down, then the acceleration, or you pull it down, then we are below the equilibrium position, and it goes back up, that spring is compressed. So if you have a spring, I guess because I grew up where we didn't have internet and didn't have smartphones, I played with springs and shit. I mean, the stuff I did. My dad was so upset at the number of tools we destroyed as kids because, you know, we didn't have internet. We'd go play in his garage, and he was so upset. By the way, come-alongs and pulleys are not made for you to use as swings, just so you know that. I found that out later. Anyway, so if we had a spring here, it'd be really cool if I did, it's at rest with a mass on it. And then you pull it down, and then you're going to let go. When you let it go, it comes back up and it compresses that spring. So when you're in the up position above equilibrium, you are just simply above the level of equilibrium, and the spring is compressed. So down, the spring is stretched, and up, the spring is compressed.
What is the x of t?
When we're talking about x of t, it is the distance traveled from equilibrium based on the time.
Which one is which x?
So x is a function now, and it is in reference to t. So x is not an input. X is, we call the function x. X is the function, and it is the distance traveled in respect to the time it took to get there. So let's go through an example here, and I've got all the answers here too, so we can just talk about them. Suppose you have an object that weighs 10 pounds. It is suspended from the ceiling that has a spring that stretches 2 feet from equilibrium when the object is attached. So find the spring constant. So the first thing you need to do is find how stiff is this spring, and that's the spring constant. The way in which you determine how stiff it is you use the fact that F is equal to KD. So we have the 10 pounds. 10 pounds is a force. It is not a mass. 10 pounds, when you see pounds, that is a force. It is not a mass. Pounds is a force. And we know it stretches 2 feet from its equilibrium position when it's attached. So before the spring gets stretched, because you put a weight on it, it has it's whatever distance is. You put that weight on there before you even pull it down. When you put that weight on there, it goes down 2 feet. So using the fact that the force is equal to kd, remember when you see pounds, that is not a mass, that is force. So 10 pounds is equal to the spring constant times the distance it traveled from equilibrium once you put that weight on there. So my spring constant is 5 pounds per foot. Yes?
Would it be feet squared?
Just feet, because it's a linear distance. Yep.
So K means how far it stretches per unit weight applied?
Yes, the spring constant is how stiff the spring is. And it is a pounds per foot, or it is a kilograms per meter, or whatever your units are.
So is it the same thing if the same amount of force required to compress it that same distance?
Not necessarily. I'm going to go with yes for right now. How about that? In physics, you'll explore it further. How about yes for right now? Your physics teacher will say, oh, not necessarily. So the other thing I need is my weight. Well, the weight is just, or my mass. I need my mass. So my mass is just my weight, which also happens to be a force. So it's my mass times gravity. So remember, 10 pounds is my force. It is also the weight, because it tells me it is 10 pounds in weight. And so I found the mass, which is 10 over 32, which if you want to, you can reduce that. Any questions so far?
Yeah, can you just say that W again?
So weight is mass times gravity. So when you get up in the morning and you weigh yourself and it is whatever your weight is, let's go with 100 pounds. So if you weigh yourself in the morning and you weigh 100 pounds, or you weigh 150 pounds, or whatever you weigh, that is not your mass. That is your weight. Your mass is something different than your weight. So the mass you have right now is going to be the same mass you have if you were on the moon, if you were out in space. Your weight on the moon is going to be considerably less than what it is here because your gravitational force on the moon is considerably less. But your mass has not changed.
So we multiply the mass times the gravity to get the weight.
Yes. And remember, weight is a force as well.
And what's the mass again?
On this one, the mass,
Yeah, like how we calculate the mass? So multiply it by the gravity?
that's how we calculate the weight.
Yeah, but how do you calculate the mass to multiply by the gravity to calculate the weight?
There's a lot of ways to calculate the mass.
But how do we do it? For this?
If you want to just calculate mass, is that what you're asking me?
Yes, so we can do these problems.
Oh, so you want to find the mass?
Yeah.
Okay, I get you. I'm tracking now. So what we use is this formula right here that says my weight is equal to my mass times gravity. So I'll be given either mass or I'll be given weight, one of the two. I'll be given one of the two.
Right.
So in this case, I was given the weight, but I need the mass. I need the mass, and the reason I need the mass is because my formulas up here use mass.
Yeah.
So I need the mass. I don't need the weight. I need the mass. Okay? So I had to find the mass first. And I also had to find the spring constant K because that also is one of the things I need up here. See, I need that as well. I need that K, and I need the mass. I need the spring constant if it's not given to me, and I need the mass if it's not given to me. So this intermediate step is stuff that I have to do if I'm not given the mass and I'm not given the spring constant. If I'm given the mass and the spring constant, I don't have to do what I just did.
So it looked like down below the mass was the weight divided by the imperial.
So yes, my mass is my weight divided by my gravity. Since my weight was given in pounds, then I used the imperial gravity.
And then that gives you, and then you end up multiplying by gravity again.
No.
Okay.
No, we know what weight is. We don't have to find weight. What we're chasing is the mass. We're chasing mass on this one. We're not chasing weight. Weight's given to us.
Did you say
Yeah.
Is that because it's multiplied by gravity?
Yes.
Gravity force?
Yes. Yep. Okay, so now I want to find the equation of the motion of the object if it is released from 1 foot below the equilibrium position from rest. And then we want to find the time in which the object passes through equilibrium and its direction it is heading. Okay? So the first thing we're going to do is we need to find that omega. Omega is going to be equal to my k divided by m. For this particular example, we found k to be 5 and our mass to be 10 divided by 32. And so I put that on my calculator and 4 kicks out. So I found my omega. That's the first thing I need. Once I find my omega, I'm going to use that formula that says I need to find what A is. Well, A is going to be x naught squared. That is where I'm going to pull the spring down to. So I'll let go, pull that spring down. And then plus my initial velocity. We are not given an initial velocity, and what I'm doing is I'm pulling it down and I'm holding on to it before I let it go. Because I'm holding on to it before I let it go, the initial velocity is 0. It won't be 0 later, but initial velocity on this case will be 0. Yes?
What was the
Omega?
omega again?
So omega in the past for us, when we go back up here, in the past, omega has simply been the, when we looked at it in the past, we had omega right here, right? Omega was your period change. So omega here is found by using the spring constant divided by the mass and the square root of that. Yes?
When you said x naught squared, can't we just write x instead of 2 to 0 and anything?
Okay. So the question is, when I'm doing this, can't I just do x? And no, the answer is no, because I need to know what x naught means, my initial starting position.
X naught.
So x naught, x sub 0, is my initial starting position. And then I need whatever that is to square it. So if I pulled that down more than a foot, say I pulled it down 5 feet, then x naught would be 5 squared.
Okay. I thought you meant x is not squared, but it's x naught. Yeah.
We're good?
Yeah.
Okay, and v naught is the initial velocity. Now remember, I'm pulling this thing down and I'm holding on to it. My initial velocity is 0 because I am not pushing it up when I let it go. I am just letting it go. Like Elsa, just let it go. You knew that was coming. You knew it was coming. Yes?
I don't know if I'm just missing something, but where did you get x naught from? Where it's a line, where's the field from?
So this says that I am going to pull this object down 1 foot before I release it. This was not the day you wanted to skip. If there was a day, it's not this one. It would be a negative number, but it'd be squared, so it's still 1.
Can you make it be the C also?
Yes, Amy.
What's the, you probably already said this, but what's the, fee thingy?
This fee?
Yeah, that symbol.
Yeah, what is that?
Fee. I don't know. I'm sorry. I'm not being a smart ass. What are you asking me?
What does it mean?
Oh, so what that is, let's go back up to the formula here. So that fee is this fee. It's just wrote different. It's just it's a different way of writing it.
Is there a phone and a phone?
Fee, fi, fo, fum. It's just the angle.
So it's like the alpha and the beta kind of
Yes.
thing? Okay.
Yes. Yes. Okay. Anything else? These are really good questions. What else do you have?
I'm just trying to write it. I'll write it down.
Do you have a question?
I'm just gonna, so if there is never, if all the time, if you don't know velocity, it's always gonna be 0.
Yes.
Okay.
Yes. So the question was, if you don't have an initial velocity, like I'm not throwing this thing up in the air when I release it, it's always going to be 0. The initial velocity is going to be 0. In this case, I'm holding it, and then I release, and so my initial velocity is 0. The other thing we have is I'm trying to figure out what my phi or alpha or beta, whatever you want to call it, is. I'm trying to figure that out. And so I now found out what A was, right? A is my amplitude. So A is my amplitude. We found that by doing my initial position, my initial velocity, and my omega. So I use this formula right here that says A, which I found to be 1, times the sine of phi, which is just an angle, is equal to my initial position. So 1 times the sine of phi is equal to 1. So where does that equal? Well, where is the sine of any angle equal to 1 on the unit circle? Pi over 2. Does that make sense? Pi over 2. Now if my A, as an example, if my A was, say, 2, this is a different example. If my amplitude was 2 instead, then I would have had 2 times the sine of phi is equal to 1. The sine of phi is equal to, I used theta there. The sine of phi is equal to 1/2. And so my angle would not be pi over 2. So it's not always going to be pi over 2. Whether or not it's pi over 2 is based on my initial position and my amplitude. Because those are equal, then my phi, or my angle, is pi over 2. So my formula, putting everything in the right places, is this. I'm going to go back up to the formula so you can see I've just put everything in the right places. So again, my formula is this. Right here. Here's the formula I'm looking for. I needed to know A, which I found. I needed to find omega, which I found. And I needed to find phi, which I found. That is going to give me the distance relative to the time. I had to do a lot of steps to get there, though. Unlike our previous one, where I can just look at the maximum and the minima and how long did it travel, we don't have that information. We don't have the graph. So once I have all of that information, I just put it into that formula, and I get this. X of t is equal to the sine of 4t plus pi over 2. And I found all that information by those intermediate steps. There's a lot of steps to take to get to that point. So that's the equation of the function of where the object is at some time. Yes?
Will we have to memorize all these equations?
Oh, hell no.
Okay.
I mean, oh, heck no. Better delete that later. Yes?
So once you get to that, do you like factor out the omega and all that normal stuff?
You can. We're just going to leave it for right now, though. Yes?
So we only use like the slope thing when there's weight or mass?
Yes. Yes.
So what do we do once we have it?
So now we have the equation, right? Now that we have the equation, at 1 second, I can tell you where it is. At 3 seconds, I can tell you where it is. At 10 seconds, I can tell you where it is. So now that I have the equation, I can tell you the position with respect to time if I know the time. What it's asking me, though, is where is that equal to 0? So I'm at 0, the equilibrium position equation, or this equation should equal 0. So I set the equation equal to 0 because I am at equilibrium. And now I did my regular solving that I did in 10.7. So I'm going to take the sine inverse of that. So I know that when sine is equal to 0 on the unit circle, where is the sine equal to 0 on the unit circle? 2 pi, also where? Pi, also where? 0. So the places in which this thing is equal to 0 is when my angle, I'll call it alpha this time, when my alpha is equal to 0, pi, or 2 pi, and multiples of pi, right? So we know this alpha, we'll call it alpha if you want. Alpha is equal to pi k. Do you agree to that, pi k, multiples of pi k? Now, I don't have alpha though, what I have is 4t plus pi over 2 is equal to pi k. So just like I did in 10.7, is my angle, which I called alpha just as an intermediate, and then I actually have to put that angle in there. My angle is this. My angle is not alpha, my angle is that. So then I just solve for t. And so I subtract pi over 2 from both sides, and then I divide by 4. And I'm looking for the very first time this happens. I want the very first time this happens is when I'm at equilibrium. That's when I want to know that. So I'm going to go ahead and take this 4t is equal to pi k minus pi over 2. Now what? Divide by 4. How are we doing so far? When I divide by 4, it's the same thing as, and I should have been doing this in a different color. When I divide by 4, it's the same thing as multiplying by 1/4. Dividing by 4 is the same thing as multiplying by 1/4. So 1/4 times 1/2 is 1/8, so pi over 8. So this is my final answer with the exception of the fact that I need to start when k equals 0, and that will be my final answer. So k equals 0. So this is it. But there's a negative on there. Now, we got to talk about what the negative means. Negative means direction. Down is positive. Up is negative. Because it was a negative pi halves, it means that we are in an upward motion. Down is positive, negative is up. So if you didn't have enough problems about left, right, up, down, clockwise rotation, counterclockwise rotation, here's some more to mess you up. Down is positive, up is negative, yes.
Is it an easy way to think about this as like gravity? When things going down is normal, that's positive?
Yes. Yep. So my final answer is pi over 8, or in other words, 0.39 of a second it takes to move upward from the down position to the point of equilibrium.
You don't have to write negative?
No, because negative means is up. So negative, when we see negative, it means that we are going in an up position, we're going moving upwards.
But it says upward right there.
Right. So we ended up with, when I put k equals 0, t is equal to negative pi over 8. That negative tells me I'm going up. That's what it means. If that would have been positive, I would have been coming in a downward motion. Because it's negative, it's now telling me directionality. You'll love this in calculus.
Just think the opposite of gravity or something.
Yeah, well, if it's negative and we're going up, how's the answer not negative pi over 8? Like,
So the negative tells us direction, or positive tells us direction.
yeah, and it says that you're going up, that's direction.
Right, so so over here, right, I did not put that negative there because it is pi over 8, but it's a negative pi over 8. Because it's negative pi over 8, it means it's pi over 8 up. Yes.
So basically, when you write upward, it's replacing the negative.
Yes. Thank you. Sometimes as an engineer, recovering engineer, I make it way harder than it needs to be. And this is one of those cases. Are you okay?
Yeah. So good.
That's all good. So let's take a look at another example here. So in this example, we want to find the motion as released 4 inches above the equilibrium position with a downward velocity of 2 feet per second. So the first thing we have to do is find omega. We have to find omega. We need that omega so that we can put it and find my amplitude. Once I find my amplitude, like I did before, I use this equation here to figure out what my angle is. It is my amplitude sine phi is equal to negative pi, or negative 6 over 12. Once I do that, I get my angle. Once I find my angle, I also need to find which quadrant I'm in. So this is the first time I use this formula. I use this formula to determine the quadrant that I am in. And then I bring all this lovely together, and there's my final 2 answers. It is this here, and then I solve, and it is this here.
So the x naught is the equation that you did to get A? On the second line?
X naught.
Yeah, that you have circled in the black box.
So X naught, so a couple of things that are going on here is, let me get rid of some of the stuff I just wrote so I can go back to it. So we have 6 inches. So we have a couple of things that are going on. The first thing is that we have a unit conversion from inches, and I'm getting information in feet. X naught, in this case, is where do I start? Well, I start in an up position, so that is a negative 6, and I have to convert it into feet. So negative 0.5 of a foot. So x naught is always my starting position. In this case, my x naught happens to be negative 0.5. Negative because I am in an up position, and because I have to do that conversion from inches into feet. So that's where the x naught here comes from. That's why it's a negative 6 over 12. Negative because I am upwards, and I have to convert from inches to feet.
So when you say to find phi, we have a sine equals phi equals x naught.
Yep, so this x naught is the same thing here, which is the same thing here. Those are all the same thing. X naught is the initial position, and in this case, I told you I am actually compressing the spring, and then I'm forcing it down at the same time because I'm saying that I have an initial velocity. So it's not like I'm compressing the spring and letting go. When I'm letting go, I'm pushing it down with a velocity of 2 feet per second as well.
Okay, so what does that mean then? You have a sine of phi equals x naught. Like, a is like that big long equation. And that's
Above it, yeah, that's what I have to do to find A.
Came out to root 2 over 2, but you're saying that x naught is negative 0.5.
Okay, now I know what's happening. Do you agree that this is a perimeter equation?
Yeah.
What if I were to tell you the length is equal to 12 and the perimeter is equal to 250? What would you do with that information? Stuff. What would you do with the 12? Where would you put it? So you would replace this with 12, right? What would you do with the 250?
I would subtract 24.
You would put it right there, wouldn't you?
Yeah.
Okay, so we have this equation that says A the sine of phi is equal to x naught. What if I were to tell you that a is equal to negative, or it's a square root of 2 over 2, and I were to tell you that x naught is equal to negative 6 over 12, what would you do with that information? What would you do with the a? Where would you put that square root of 3 or square root of 2 over 2? Okay, so you would put a right here, right? What would you do with the x naught? You would put the x naught right there, yes? Okay, so you would write this as a square root of 2 over 2. The sine of phi is equal to negative 6 over 12, right? Isn't that what that is right there? Okay. Does that answer your question? All right. So once I've done that, I solve for phi like I normally do with inverses or look on the unit circle where this makes this a true statement. Once I look on the unit circle where this makes it a true statement, I do need to know whether or not phi is equal to 5 pi over 4 or phi is equal to 7 pi over 4. This is an extra step I didn't have to do in my previous example, because on my previous example, I just had phi is equal to pi over 2. It's only going to happen at pi over 2. So on this one, I have to find out where it is. Which quadrant are we in? So I use this second equation I didn't have to use on my first one to figure out which quadrant I'm in. Okay, so I have to figure out my quadrant. Am I in quadrant 3 or am I in quadrant 4? Well, I know that it ends up being a positive answer, right? So I put everything in the right places and I end up with a positive answer. That means I'm in quadrant 4 because that is the two choices. My first choice is in quadrant 3, which is 5 pi over 4. My second choice is in quadrant 4, which is 7 pi over 4. So I use the second equation that I didn't have to before to figure out which quadrant. Well, it has to be 7 pi over 4 because cosine's positive in two places, 1 and 4. 1 was not a choice, has to be 4. 1 was not a choice, it has to be 4. So then here's my equation right here. There's my equation. That's one thing that I was chasing. The other thing I was chasing is how long does it take to hit equilibrium? Now when I do this, I do the same thing as I did before, and I end up with the 4 pi plus 7 pi over 4 is equal to pi, or k pi if you want. And I know in this case it's going to be 3.34 seconds, how long it takes to get there. 3.34 seconds, and it's positive. That means we are in a downward position. So that is the end of this section. Would I expect any of you put this on this test? Oh, please don't. Because this is a question that if it took me 20 minutes to go through, just think how long it would take one of you to if you put it on a test. It hits a lot of information, but this would be a really good take-home test question. It would be a really good project question. It would be a really good quiz question that you took home, but it is not a good test question. Please don't pack up because we're going to start the next section. We are starting the next section. It will be delicious. So let's take a look again at the square root of 2
for negative 1/2. And
so no, let's go back to the square root of 2 sine phi, which is what we're trying to solve for, is equal to, I'm going to write this as negative 1/2. Is that okay?
Oh, yeah, and this is like what we were doing before in your office, right? So you were
Okay.
saying like this produces...
Negative 1/2, thank you. I'm going to multiply by the reciprocal of this, which is 2 over the root 2.
Okay.
Right? Those cancel, and I get the sine of phi, and I keep on right theta, is equal to negative 1 over the square root of 2, which is negative square root of 2 over 2. So that means that phi has to be a 45 in quadrant 3 and quadrant 4.
So this says that...
If we take a look at this, and I have the square root of 2 over 2, the sine of 4t plus 7 pi over 4 is equal to 0. I'm going to multiply both sides by the square root of 2 over 2. And so I have the sine of 4t plus 7 pi over 4 is equal to 0. So where is the sine is equal to 0? Well, the sine is equal to 0 when I'm at multiples of pi. So 4t plus 7 pi over 4. Okay? And that's how we got it.